Hello there and welcome to our Global Illumination Workflows for Design Visualization, Lightmass and Beyond course. My name is Joe Bradley and I'm excited to have the chance to show you around the powerful GI tools that can be found in the Unreal Engine. Tools that can help us create fantastic looking lighting solutions for our visualization projects. To get started, we will first of all take a look at how level setup in the engine can influence the lighting solutions that we produce, and at how our GI solutions are both created and stored. We will see how we can focus GI calculations so as to be sure that our computing resources are being put to best use. We will also look at how materials affect our lighting solutions, and at the light portals and quality settings that can help us produce GI solutions that are clean and production ready. Once we have our GI in place, we will move on to creating area shadows and looking at lighting our level with HDRIs, before moving on to ambient occlusion and a consideration of how adjusting the static lighting scale in a scene can affect the quality of the GI that we produce. By the time we get to the final section in the course, we will be ready to take a look at important topics such as how to handle animated objects with GI, and at adding finishing touches to the baked lighting we've created by means of post-processing effects that can directly affect our GI solution. To close things out, we will look at how we both create and control color bleed, create and use lighting scenarios, and then finally at how we would go about saving out some high resolution stills from the engine. As we have lots of important topics to cover, I am sure you are ready to dive right in and start setting up our project. Although I will be doing my best to let you know where features can be found in the Unreal UI, and to call out any keyboard shortcuts that I may be using, I am still approaching this course with the assumption that you have at least a basic knowledge of Unreal, so the layout and workings of the UI, the scene navigation tools, and so on. A basic understanding of Unreal's lighting tools would also help you get the most out of this course. If you are completely new to the Unreal Engine and so need to become familiar with the interface, light types available, and so on, then perhaps some of the more foundational courses that have been created by Epic Games would be a good place to start, before going ahead and working through this course, that is. As we will be covering both the creation and refinement process for creating a good global illumination solution in the engine, no prior knowledge in this area is needed, as by the end of the course, we will have shown you how to start getting the best out of this very powerful set of Unreal lighting tools. If you have access to the files that are provided with this class, then you will be able to follow along with the steps that are shown in the video presentations found here. In fact, in the very next video of this chapter, I will be showing you how to both set the project up and make best use of it. For my personal ease of use, I have placed the class files on my desktop, but you can of course store them in any location that you like. If you don't have access to the class files, or if you simply want to use levels and projects of your own as you work along and learn, then that is completely fine. As this is a course about global illumination though, just be sure that you have your basic lighting setup in place and ready to go, and all will be well. Keep in mind also, though, that whilst you will be able to follow along with the concepts presented here using your own scenes, you will of course need to adapt the settings that are used so as to suit your particular level. That having been said then, let's move on and take a look at how we can go about setting up the Unreal project that we will be using throughout the duration of this class. Now that we have our exercise files downloaded, and in my case placed on the desktop, time to get our Unreal project set up and ready to work with. To start then, we will need to have downloaded and installed the Epic Games Launcher from unrealengine.com. And then make sure that we have the latest version of the Unreal Engine installed from inside it, which in my case is 4.19. After which, we can click the launch button and boot up the engine, giving us the ability to go ahead and create a new project if needed. As I already have one in the class files folder, however, I am just going to click on the browse button. After navigating to the class files folder, we can click on the project file in order to open it. Once inside the project, you can see that we already have multiple levels set up inside the content browser, specifically in the maps folder. These have all been named according to the video exercises to which they correspond. Some presentations will have multiple levels that need to be used, and so these have been given a letter suffix that just determines the order in which they need to be loaded, with a simple double click on the level in the content browser being enough to load it up. Now, if you don't have access to the actual class files that I'll be using, you can still grab the original project and so follow along with the course in that way by coming back to the Epic launcher, and if we click to enter the Learn section, you can see that we have a number of useful projects ready to be downloaded. Scrolling down the list, the one that we want here is the realistic rendering example. And if we click on this, we can then choose the engine version that we want to create the project for. Now, of course, this particular project doesn't have the exact same setup as the one that I will be using from the class files download, but it does certainly give you the same basic platform from which to set up a version of your own. Well, now that we have the project set up and ready to work with, let's dive in there and take a look at the stuff that we will be working with as we move through the course. As we work through this course together, our ultimate goal will be to gain an understanding of which, out of the many tools available in Unreal, can help us really get the best out of our global illumination solutions. Before we get started though, there are just a few aspects of the scene or level setup that we're working with here that needs to be discussed, just so that you understand what we already have going on. First of all then, we need to understand that the engine settings applied in the realistic rendering project, which of course was the starting point from which our class files were built, are, well, not the defaults that you would get in Unreal if you were to create your own new project from scratch. But these are the settings that we will be working with as we move forward. So, whether you are using the class files that came with this course or have downloaded the realistic rendering project from the Epic launcher, we should all be working with the same basic engine settings. In terms of lighting setup, there are of course lots of ways in which we could approach the setup of our lighting in Unreal, especially so given that it doesn't currently have a daylight solution that works with physically correct, real-world values in the way that, say, the V-Ray sun and sky combo does. Because of this, I'm going to be leaving the direct or sunlight that is set up in the scene at its default intensity value of 10, and then work at building a GI solution around that setting. Any other lights that I use during the course or any changes to intensity settings that I make will be called out as we go. Which brings us nicely onto the fact that our scene has also been set up with a post-process volume already in place. The reason for this is so that we can set a constant rather than changing exposure, as seen here in the eye adaptation values, both of which have been set at 0.25 so as to work with the default sun intensity. We have, however, turned other post-processing effects such as bloom and vignetting off, as these could potentially obscure our lighting solution. Of course, we will come back to the post-process controls later on in the course so that we can see how to add these effects back into the scene should we want to use them. Coming back to our sunlight, one important fact that we need to know is that this has been set to be a static as opposed to stationary or movable light. Now, we will look at some of the reasons why static lights are good to use with global illumination a little later on in the class, but the big reason, and one that is worth making clear now, is the fact that movable or fully dynamic lights, as they are sometimes called, do not generate or contribute to a baked indirect lighting solution. In other words, they will add nothing at all to our GI solutions. Stationary lights, on the other hand, are included in the GI calculation, but if a change is made to their intensity or colour at runtime, then we won't actually see this show up in our GI. So if, for example, we have a white stationary light turn red at some point, maybe via a blueprint trigger in the level, the actual GI in the scene will still show it as being a white light. Just something worth keeping in mind. The Lightmass settings in the levels have all been left at default, but again, if and when we change that at all, I'll be sure to call it out. One change that you will see occur on a regular basis as we work through the exercises is the fact that with our viewport in focus, if we press the G key on our keyboard to enter game mode, you can see, because lighting is baked at runtime, that there is a difference between the viewport and runtime lighting, and so always be sure to test your lighting solutions using the game mode in the viewport. As regards the camera, if we come to the viewport type dropdown, you can see that we're using the cinematic camera mode here, which just gives us a nice framing for the camera shots that we have set up, although this can of course be altered at any time if you would like. In the build dropdown, the lighting quality that we will be using as we work through the class has been set to production so that we can straight away see how the options that we change are affecting the final GI setup. Now, this obviously is not a workflow that we would want to use in a production setting, so feel free to use the preview quality setting if you prefer, so as to speed things up as you follow along. We also, as I have already mentioned, have some bookmarked camera views set up that we will be switching between as we go. Cycling through them is easy enough, so if we press the 0 key, we have our main shot. Pressing 1 gives us a view that focuses on direct sunlight. 2 has us looking at some of the hard to reach places for GI, and 3 just pushes in for a close-up of these. Finally, our scene has had a plain grey material applied to all of the geometry so as to help keep visual clutter down. Although we will talk more about materials and how they affect our GI solutions later on, with some of the final materials used at the end of the course having been modified a little from the realistic rendering project so as to fit more in line with some of the concepts that we will be discussing. As I am sure you are eager to dive into the global illumination tools and examine their workings in Unreal, let's end this exercise there and move on to our first look at the Lightmass renderer. Before we can create a good global illumination solution in Unreal, we need to understand at least a little bit about what Lightmass is and how it works, simply because it is Unreal's way of calculating and storing indirect lighting information. Whenever we come to the build menu then, and use any of the lighting options found there, it will be the Lightmass renderer that performs the GI calculations, and the Lightmass renderer that will then create lightmap textures for each and every object in the scene, with these maps containing all of the complex lighting and shadow information found inside the level. Communication between the Unreal Editor and Lightmass is handled by the Swarm agent, which essentially manages the lighting build as it is compiled. So, if we are working on just a single machine, the Swarm agent will take care of core and thread management. But if we instead have a network of machines available, it can also distribute the lighting calculation across as many remote machines as we have available. With our project open and the level 01_02 loaded up, if we come to our build options, make sure that we are set to use the production option and then click the build lighting only option, we will see the Swarm agent engage. Coming to our Windows application tray, we can see that it is running minimized, and we can double click to open it up if we want to see exactly what it is doing in terms of resource management. What we can do now is see exactly which machines are being used by Unreal for the light calculation, what part of the process they are working on, and how many threads are actually being used for them. Indeed, if we use the middle mouse button to roll upwards and focus in, we can even see the different steps that the Swarm agent has and is taking. So, first of all, we see that Lightmass starts up. It then emits direct photons, or the first bounce of light, after which indirect or secondary bounced photons were calculated. It then moved on to irradiance photons, which it caches, calculated skylight radiosity, and then finally it will go ahead and bake all of this information into light maps. We can see what these light maps look like once the build is complete if we want by coming to the World Settings tab, scrolling down the options list until we come to the Lightmass rollout, and then clicking the small expandable arrow where we see our light maps rollout and the baked results of our lighting. So, whilst we have by no means taken an in-depth look at the workings of Lightmass, hopefully this quick overview has given us at least a basic understanding of how the Lightmass process works, as this will come in useful later on in the course when we start trying to get as much quality and speed out of the renderer as possible. Because Lightmass uses bitmaps to store both direct and indirect lighting information, the creation and placement of Lightmap UVs on our meshes will have a direct impact on the quality of our global illumination solutions. Two important questions to both ask and answer then are 1. How do Lightmap UVs actually work? And 2. How can they help make our lighting solution look good? To help answer these, if we come to a static mesh in our content browser, so Content, ArchViz, Mesh folders, and double-click to view, let's say, the couch_1-seat mesh, we automatically open up the Asset Viewer, where we are able to see the Lightmap UVs for this object. Let's select the mesh in the viewport and then press F to focus in on it. At the top of the UI, we have a UV button with a drop-down arrow, which, if we click on, instantly shows us that our object has 2 UV channels assigned to it. Channel 0 contains UVs for materials and any associated texture maps that may be applied there, whilst Channel 1 contains our Lightmap UVs. Why do objects need separate UV channels, though? Well, we have already said that when using GI, our lighting will end up being baked into bitmaps, with every part of each mesh found in a level needing to capture and store the subtleties of the lighting found in its surrounding environment. Now, because of the way that photons will be bounced around the environment by Lightmass, the chances that lighting information found on the various parts of an object's surface will be identical to any others in the scene, well, it's almost non-existent. But, of course, texture artists will typically want to stack UV islands or clusters on top of one another in order to squeeze as much resolution out of a texture map as possible. In other words, they may be happy to repeat information in multiple places on a static mesh's surface. As lighting artists, though, we need to have separated UVs for the light maps because each part of the lighting solution is completely unique. Now, it is possible that when importing meshes into Unreal, we may find that the wrong UV channel has been assigned to the light maps. So, how might we go about changing the UV channel assignment in Unreal if that has happened? Well, if we come to the LOD0 section of our model and take a look at the base settings, we can see 2 options that we are interested in. Source Index is the UV channel that Unreal will look at in order to create Lightmap UVs if they don't exist. In other words, this will typically be the default UV channel assigned for material work. If we have no Lightmap UVs then, and so need to create them in Unreal, then this setting will need to point to the channel being used for the texture UVs. The second option, Destination Lightmap Index, tells Unreal which channel to place newly created Lightmap UVs in, usually channel 1, as most models will have only a single UV channel already assigned. If our model has multiple UV channels, then we need to set this to a channel number not currently being used. If this is all perhaps a little confusing, don't worry, as we will be looking at how to generate UVs from these controls in the very next exercise. Although creating Lightmap UVs for every static mesh in your level may sound like a lot of work to get through, we do actually have a couple of options available to us for getting it done as we work through our project. The first would be to manually add a second UV channel in a DCC application, such as 3ds Max or Houdini, and then make sure that every part of the mesh we are working on has a unique UV cluster or island. An approach that probably gives us the greatest artistic freedom and control, but one that is also potentially the most time-consuming. We could also create our Lightmap UVs right here in Unreal if we wanted, with the engine actually making it a fairly quick and painless process. The easiest approach being to check the Auto-Generate Lightmass UVs option as we import our meshes. With an Explorer window open then, we can see that inside the project folder, so Global Illumination 4.19, Content and FBX folders, we already have an FBX mesh ready and waiting. If we click and drag this onto our Unreal Content browser, after a few seconds, we should see our cursor update with a plus sign appearing next to the cursor icon. Once we see that, if we let go of the mouse button, Unreal will start the import process for us and pop up the Import Options dialog. Inside the mesh rollout, we should see an expandable arrow, which, if we click, shows us all of the options that are available for the incoming mesh, one of which is a checkbox entitled Generate Lightmap UVs. Let's uncheck that for now and click to import so that we can see how we might also go about creating Lightmap UVs from inside the asset browser itself. Now just be aware that we may need to close out any message logs that appear here. Double-clicking on our newly imported static mesh entry should launch the asset browser for us, whilst dropping down the UV button flyout should show that we only have a single UV channel applied. To fix this, we want to come to the Details tab and again locate the LOD0 rollout. In here, we have our build settings rollout that we can expand if needed, and again see the same Generate Lightmass UVs option found in the import dialog. Let's click to enable that, and then click the Apply Changes button. By default, Unreal will use the UV mapping found in the first or default channel, which reminds us that a proper job done on our UV unwrap in a DCC application can both save us time and hopefully help give us a better final result. If we check the UV drop-down again, we should find that we now have a second UV channel showing up. We have a min lightmap resolution option here that, as we increase to, let's say, 1024, and reapply our changes, enlarges the UV clusters so that we can squeeze as much quality out of the light maps as possible. We can even force a resolution change to an object's lightmap UVs if we wanted. So let's add our object to the scene, and with grid snapping set to 1, place it on our floor. One way to force a resolution change is to select the object, come to the Details tab, and after scrolling to find its Lightmass settings, click the Override Lightmap Res option, meaning we can now set a higher lightmap resolution for just this object if needed. Or if we have multiple objects selected, we can change the resolution for all of them at the same time. As doing this can greatly affect build times though, we will only want to add a resolution increase to objects that are in areas of the scene that have high contrast changes in lighting, such as transitioning from a patch of bright sunlight to a shadowed area. Of course, using the very same controls, we could also go through our scene and set less important objects to have as low a lightmap resolution as possible, which would hopefully help balance lighting build times. The only objects that I have changed in this way here, as compared to the original realistic rendering project, are the walls, floor, and ceiling geometries, which as you can see have been set to a resolution of 1024, the doors, which have been set to 512, and the carpet, curtains, and tables, which now have a value of 128. These objects have been set to a higher resolution in order to help make changes from the values we adjust easier to see as we perform our lighting builds. Again, do feel free to set these as high or as low as you like. Although, if performance is an issue when creating lightmap UVs, then we may find ourselves needing, depending on object density in our scene, to lower some lightmaps to as low as 8x8 or 16x16 for smaller objects. Now, keeping in mind that the lower the lightmap resolution we use, the more padding we will need to leave between the UV islands in order to help prevent light bleeding from one island to another. The padding that we may see around the edges of the lightmap UV layout isn't actually needed, as Lightmass automatically adds enough padding around the edges to prevent bleed artifacts by default. When creating Lightmap UVs in a DCC application, it is good to keep in mind that the more UV islands we have, the greater the chances of lighting artifacts appearing. Whenever possible then, we will want to try and keep any edges connected on the visual mesh connected in the Lightmap UVs as well. As an example, in the UE4 documentation, you can see that this first object here is using lots of unconnected UV islands in the Lightmap, and so is causing the mesh to display drastic changes in lighting on each face of the geometry. Whilst the second object has connected as many edges together as possible, especially edges that are visible to the user, thus giving the Lightmap greater consistency and quality across the geometry surface. If we are instead importing objects into Unreal using Epic's Datasmith toolset, then just as when importing an FBX into Unreal, we can again generate Lightmap UVs automatically by putting a check in the relevant box. Although UV creation may not be the first thing on our minds when looking to create good lighting and GI in Unreal, you have hopefully grasped that it can make a huge difference to the final product, possibly the difference between an okay looking and a fantastic looking visualization. Depending on the nature of a project, it is entirely possible for us to be working on a scene, most likely an ArchViz interior, that has a landscape mesh reaching out to the edges of the editor grid, whilst at the same time having a much smaller playable or walkable area that needs a high quality lighting solution applying to it. Now, because Lightmass emits photons based on the overall size of a level, that outdoor mesh, which is after all just a background object, will greatly increase the number of photons that the renderer emits, having the knock-on effect of increasing light build times by quite a bit. To help combat this problem, we have the Lightmass importance volume, which can be accessed from the Modes tab under the Place and Volumes options. Or we could, of course, simply type Lightmass into the search field and then add an importance volume to the scene by means of a simple left-click and drag operation. What this volume controls is the area inside which Lightmass will employ higher quality settings. Why is this good? Well, because it essentially lets us concentrate lighting calculations to the area or areas in the scene that need a detailed lighting solution. Areas outside the importance volume, so let's say outside of the window in the distance here, will receive just a single bounce of indirect light as compared to the multiple bounces that we may have going on inside, and this will happen at a lower quality than areas inside the importance volume as well. What though if we have a level with multiple rooms that all need high quality lighting applying? Well, we can actually place multiple Lightmass importance volumes in a level if we need to, although we will need to keep in mind that the final lighting build will be calculated inside a virtual bounding box that contains all volumes, and so the more of them we have and the more spread out in the level they are, the more adversely our light building times will be impacted. Volume lighting samples, however, which we will be looking at later on in the course, are only placed inside the smaller volumes, and so if we are going to be using those in our visualization, then it may well make sense for us to use smaller, more localized importance volumes. What we want to do now then is scale our volume so that it fills the area of the scene that needs detailed indirect lighting applying to it. For the sake of speed then, I am just going to enter location values here of 130, 0, and 150, and then scale values of 4, 7, and 2. All that is left to do now is set our bake quality to production, if it isn't already, and then go ahead and build the lighting solution. The Lightmass settings are set to default here, but don't worry, as we will be looking at these throughout the course and figuring out how we can improve on them as needed. Now, whilst in a comparison between the scene with an importance volume applied and the scene without, we can see a subtle difference. The improvement this brings will become even more noticeable after our next exercise, because having gotten the photons and Lightmass calculations focused where we want them, it is now time to take a look at our light's secondary bounce controls. Although we do, by default in Unreal, always have global illumination set up in a new project or level whenever we create it, we are probably going to want to know how to fine-tune the amount of light bouncing around an environment, so that we can then tweak and art direct the lighting to suit our project's needs. With our 01_06 level loaded then, let's come to the World Settings tab, where we see that this particular version of the scene has just a directional light set up. Let's see what kind of global illumination solution we can get out of it as we move forward then, focusing particularly on the quality level that we are able to produce. If we come to the Lightmass rollout then, the second option that we see lets us control the amount of indirect light bounces that can occur in the environment. Of course, if we were to set this to 0, then we would see only the effects of direct lighting in the scene, as this would essentially turn off the bounce light calculation. What we are looking at then is what things would look like if we baked the current lighting setup using the production settings. Setting the value to 1, and then rebuilding the lighting, will of course give us just a single bounce of light. But notice how even that small change can drastically improve a lighting solution. 5 bounces will give us this result, which again gives us another big boost in illumination levels. And then, finally, we can set the number of bounces to 10, which, in this particular scene, now starts to produce diminishing returns, as the build here took quite a bit longer to calculate than with the bounce value of 5, and yet it only has improved our solution by a small amount. Naturally then, it will be up to us as the controlling artist to slowly increase the number of bounces being used until we have things set just right for our scene. In my personal experience, on some levels, bounces above 10 start to become a bit of a waste of computing resources, given the diminishing returns that we get. And we also need to remember that the final GI quality can also be improved by using other controls in the engine as well. For instance, just below the indirect bounces control, assuming that we are using version 4.18 or later of the engine, we now have a skylight bounce control as well. To test this, let's load the 01_06B version of our level, which in this instance is being lit by just a skylight, which can of course be created by dragging one out from the light section of the Modes tab. A skylight by default is set up to capture the most distant parts of a level and then use that to light a scene. To give the skylight something to capture here, we can simply come to the World Settings tab, and from inside the Lightmass controls, set our environment intensity value to 1, after which we can click on the color swatch and set the environment color to RGB values of 0.7, 0.9, and 1. Still inside the World Settings tab inside our Lightmass rollout, we can set our skylight bounces to 0, and then again build our lighting using the production quality setting. The result that we see now is being produced by just a single default bounce of skylight. Let's see how much skylight we can bounce around the environment then, starting with a value of 1, which is not much of an improvement really. In fact, even if we try a value of 5 and rebake our lighting, a comparison between the two settings shows that, well, we aren't really gaining anything by increasing just the bounces value. If we want to add more ambient light to the scene, then what we really need to do is increase the intensity of our light as well. Only as our skylight is capturing the environment, we won't be able to use its actual intensity control. Let's instead then come to the Lightmass settings and change the environment intensity to 10, after which we can rebake our lighting solution. Now that we are clearly adding more light to the scene, let's bump the number of skylight bounces to 10, just as we did with the directional light. Build our lighting, and then compare one last time. As with our directional light though, even after increasing the environment intensity, we are only seeing minimal change between the 5 and 10 bounce versions. Now, although it is good practice to look at how the values of both the direct and skylight bounces are working in the scene in isolation, what we ultimately need to do is blend both of them together. And so, let's open up the 01_06C version of the level, which has both directional and skylights added. And let's set the intensity of the directional light to 5. As we are using a skylight, let's come to the Lightmass rollout in the World Settings tab and use an environment intensity value of 5 as well. Whilst in the Lightmass rollout, let's also set an indirect bounces value of 7 with skylight bounces of 4. After which we can rebake our lighting, again using the production quality setting. Using both lights and their controls together now, we can easily see the improvement that we are getting by using our indirect bounces to illuminate most of the room and the skylight bounces to fill in the gaps. Of course, we will probably want to revisit the intensity settings that we have used here once we tweak the GI using the controls that we are going to be looking at, given that there is still a long way to go before we can call this a good light bake. With that said then, let's move on to yet another subject that will greatly affect the overall quality of our global illumination, this being scene materials. Up to this point in the chapter, we have managed to create a fairly decent looking GI solution that, although still needing improvement, certainly looks better than the one that we started out with. Another aspect of visualization projects that can drastically affect our lighting though, and one that we now want to take a closer look at, would be materials and textures in the scene. Indeed, as already noted, the lighting solution that we have produced up to this point has been created using just a plain grey material applied to everything in the scene. Given that this also has a fairly light base colour, and that the colour value is constant across all of the meshes in the scene, our light has been carrying quite a high energy value, and so bouncing around the environment pretty easily. Now, I am not wanting to add textures to our objects just yet, as these can make it difficult for us to accurately gauge the quality of GI that we are producing, especially so when it comes time to really fine-tuning things. Better at this point for us to get things looking good without textures, and then once we are happy with the lighting, go ahead and add materials and texture maps into the scene. What we need right now then is a way to get a better idea of just how much light will eventually be bouncing around the environment once the texturing has been done, which we can do by applying a variety of grayscale values to our objects that will either mimic or at least come close to the values that will be used in the final texture maps. Although, if we are working under some fairly tight time constraints, then even a rough approximation can still help us out quite a bit. To show what I mean, let's load the 01_07B level, make sure that we are in game mode, and then take a look at what we have, which, when compared to the previous scene, shows a noticeable change in the lighting solution. Now, we do need to note here that only the materials are different in the two scenes. Both the GI quality and light intensities are identical, meaning we can now adjust our lighting setup using this more accurate representation of how our scene will eventually behave in terms of light bounce. In this instance, let's alter the intensity of the directional light by coming to its controls, and then setting the intensity value, found in the Details tab, to around about 7.5. We can also increase both GI bounce settings by 1 in order to make use of the extra intensity, after which we can rebake our lighting solution. Not that we are done looking at the impact materials will have on our GI setup just yet. As you may have already noticed here, the grayscale values that I have used on the materials all sit within a fairly small value range. The question then is, why might this typically be a good thing to do? Well, during the light baking process, the base colour of a material will directly affect how the lighting solution ends up looking. High contrast and or dark base colours can actually make it difficult for light to bounce, with the good news being that the opposite is also true, in that low contrast or mid-range colours can make it easier to move light around an environment. In fact, a tool that can really help us see how we are doing in this department is the unlit mode of our Unreal viewport. Looking in the Unreal documentation, we have two images that can help us see the kind of difference that textures can make to GI lighting. Notice that the scene on the first image looks quite flat, and in some areas it is quite difficult to see any separation at all between the different static meshes found there. But whilst our artistic side may be telling us that things look horrible here, we really need to fight the urge to change things, because this flat look means that it will in fact be the lighting in the level that does all of the hard work in regard to making textures and the overall scene look good. Which really is how we want things to be, rather than doing things the old-fashioned way and artificially building separation and so shading into our base colour or diffuse maps. A rule of thumb that we can use to help us get good lighting in a level then is that things should always look fairly flat and boring when viewed through the unlit viewport mode in Unreal. As we say, baking lighting and shadow information into the base colour maps will ultimately only counteract the hard work that we are currently doing in setting up the lighting and GI solutions in a proper way. Now that we have an idea of how textures and materials will affect our scene then, time to move on to our next exercise and take a look at how we can use light portals to pull a little more quality out of our global illumination for an interior visualization. Although we have made a pretty good start at improving our global illumination solution, there may still be times when we need to give Lightmass a little bit of a helping hand, especially so when lighting a scene using either an emissive static mesh, a skylight, or, as we are doing in our 01_08 level, a high dynamic range image. With our lighting build set to use the production quality setting, and with a number of skylight bounces added in the world settings tab, what we see here is the result that we're getting. And as we look around the level using the bookmarked cameras by pressing the 0, 1, 2, and 3 keys, we can see that Lightmass has done a pretty good job of bouncing light around the environment. If we look a little more closely at some of the hard to reach places though, we can see that the solution is lacking a bit in quality in some areas. Now, although not a one-click solution, Lightmass portals can certainly go a long way towards helping improve the situation that we're seeing here. What is a Lightmass portal then? Well, essentially, these are Unreal actors that can be placed in a scene so as to help the Lightmass renderer figure out exactly where in the level light rays are coming from. In our Modes panel then, let's click in the search field and type Lightmass. To add a Lightmass portal, we just need to left click and drag, and there we have it. All we need to do now is place and then scale the actor so that it fits the area or opening through which light from our HDRI will be coming, which in the case of this level would be the balcony doors. Obviously, if you are using a level of your own, you will have to position and scale your portal or portals to suit. In this instance though, let's press 0 so that we can see just where we are putting the portal, and then use the transform values of 156, minus 322, and 128. A Z rotation value of minus 90, and then scale values of 10, 135, and 120, which should place our first portal right where the opening is sitting in the scene. Once we have our portal or portals in place, we can again rebuild our lighting using the production quality setting. Coming to our bookmarked view again by pressing the 3 key, and then switching the viewport over to game mode by using the G key, we can compare what we have now to our initial scene image, and see that although the change is subtle, if we look carefully at some of the books, we can see that the noise levels and problem areas have been improved somewhat by adding the portal to the scene. Not that we would want to add them blindly to our level, however, given that there is a render time penalty incurred when using them. You see, portals essentially force Lightmass to point light rays in their direction at all times, and so although we may have placed them in a part of the level that the camera can't currently see, they will still be calculated as Lightmass portals aren't occluded or blocked by geometry. Because of this, we would certainly want to avoid using portals on large or open world type levels where they may add little to no value at all lighting wise and yet still cause a significant hit in terms of light build times. With our light portals in place then, we are ready to move on and use some of the tools and controls at our disposal to tweak and improve our global illumination solution. specifically the indirect lighting quality and indirect lighting smoothness controls. So, our interior space, we are currently looking at version 01_09, has had quite a few improvements made over the course of the chapter, and indeed, for a real-time walkthrough, may already be giving us more than enough quality for the performance level that we want. There are two settings in the Lightmass controls though, that once we have our lighting mostly in place, can help us fine-tune the solution that we have by quite a bit. These being the indirect lighting quality and indirect lighting smoothness controls. To be able to clearly see the effect that these can have, however, we will probably want to brighten the overall lighting in our scene a little. And so, let's press the 3 key in order to view the darker areas of our level, and then, after coming to the World Outliner, search for the word Direct. Let's click on the directional light and set its intensity to 9. And then, in the World Settings tab and Lightmass Rollouts, set our environment intensity to 7. After which, we can rebake our lighting solution. The first of the two options that can potentially improve our finished GI at this point then is the indirect lighting quality control, which essentially scales the sample count being used by the Lightmass GI solver. Higher value settings can result in fewer lighting artifacts such as noise and splotchiness, but does come at the cost of increased build times, which is why when using this I would strongly recommend increasing the value in small increments. Just to be clear though, we do need to keep in mind that neither of the two controls being looked at here can be used to get rid of all artifacts found in a lighting solution. So for example, light map problems such as texture seams, compression artifacts and so on will all need to be fixed at the source. To see what the indirect lighting quality control can contribute then, let's increase the value to 1.25. And move on to our second option, which is the indirect lighting smoothness control, given that we will most likely want to always adjust the two of these in tandem. Simply because as we increase the indirect lighting quality control, we are essentially pulling out finer details in our lighting. And so, if we don't lower the smoothness or blurring being applied to those finer details, we will simply end up smoothing out the fine details that we've just spent time calculating. Now, although the specifics will depend on the scene that we are using, a good guideline range for the smoothing control is in the 0.75 to 0.69 range. Let's set ours to 0.7 then, and rebake our lighting so that we can compare the before and after results. Which, as you can see, now gives us more detail in the shaded areas. Time to move on to the next chapter in our class then, and take a look at even more of the tools at our disposal to help improve the quality and realism of our visualization pieces. A staple tool found in offline render engines, and one that can certainly help add realism to a final shot, are area shadows. The effect wherein the penumbra or edge of a shadow gets softer and spreads out more the further away from the light source that it gets. A question that you may ask then is how we would go about creating and controlling such shadows in Unreal. Well, the good news, given that all lights in the engine have a mobility setting located in the Details tab, is that when a light is set to static, it becomes an area light with area shadows by default. Something we will need to keep in mind when using such a tool though, is that not every light in the real world has the same amount of surface area, and so area shadow effect given to it. Figuring out which real world light types we want to mimic in our scene then, and getting to know the size of the area shadows that should be applied to them in Unreal can be critical to the believability of a finished piece. To understand how we can control the amount of blurring on our shadow penumbras then, let's take a look first of all at the Humble Spotlight. In the 02_01 version of our scene, we are lighting the interior with artificial lights in this instance. And if we press the 4 key to jump to our bookmarked camera, we can focus in on the portion of the scene that we will be using. Now, it should be noted here that as the picture frames are a focal point in this particular shot, the Lightmap resolution for them has been increased to a value of 256. Let's search for and click to select our spotlight in the World Outliner then, and take a look at the options that can be found in the Details tab. As noted, we are using the static option because by default static lights in Unreal are set to be area lights, and that is true be they point, spot, or even directional light sources. The area shape used by the spot and point lights as well is a sphere whose radius is set by means of the light source radius option. As we increase that value, we get to see the area size of the light as represented by this yellow sphere. The higher the value used here, the larger or softer the area effect on our shadows will be. If we increase this to a value of 10 in this instance then, and bake our lighting, you can see as we compare to our initial bake that used a radius of 0, that we now have much softer shadows as they move away from the light source. Let's load the 02_01B version of our level now, and press the 1 key to jump to another bookmarked camera view. Here we can see that the directional light in the scene is casting some nice long shadows. Over in the World Outliner then, let's search for the word direct, and click to select the directional light that we have. In this instance, we already have its mobility set to static, but we also need to know which of the controls found here will let us adjust the area shadows. Well, if we come to the Lightmass rollout, we have a light source angle control that, when altered, can cause our shadows to blur on the penumbra. With an angle of 0 and using a default exponent value of 2 then, all our shadows are crisp and harsh, as seen in the light build that we already have. If we set this to a value of 1 and rebake our lighting, and again compare the two versions though, we see that we are definitely getting an area shadow effect now. A value of 2 will increase this, but as you can see, if we again bake our solution, what we get is probably a little too much for this particular scene, at least in my personal opinion. Let's continue our testing using the exaggerated angle value of 2 though, as it will help us examine our next option, which is the shadow exponent. Now this control tells the light exactly when the soft shadow effect should start, in other words the distance from the receiving location to the shadow caster. Currently we have our lighting baked with an exponent of 2, but if we increase this to 3 and build our lighting, and then increase to a value of 5 and build again, we can see in our first comparison image that we have area shadow starting at about the halfway point here. But as we move to a value of 5, the shadow remains sharper for longer and then very quickly becomes blurred. Moving forward from this point then, we will be using both value and exponent settings of 1 and 2 respectively. When needing to create visualizations that will require an extra level of believability, it is going to be important that we perform careful studies on real-world light sources in order to be able to get our Unreal lights to match their look and feel as closely as possible. Knowing how to then create and control area lights and shadows in Unreal will of course help tremendously in that endeavor. When creating a visualization in Unreal, we may want to light a building exterior or interior, a product, or even a design element using a real-world environment, possibly a very specific real-world location, which in Unreal means making use of high dynamic range images to light our scene, creating a GI solution that then has lots of subtle lighting variations built in by default. To help do that, we have our O2_02 level loaded, which has had all of the lights deleted from the level, and the environment intensity setting in the Lightmass controls turned down to 0, meaning we are now in complete darkness. The Lightmass settings have been adjusted so as to give us a good GI result when using a skylight, so a skylight bounce value of 10, as well as the adjusted quality and smoothness settings that we have already looked at. We also have a light portal set up in the window opening, which will be vital in a level where no direct light is going to be applied. Let's come to the mode section of our UI then, and in the search field, type sky. After which we can click and drag to add a new skylight to the scene, and press G to make sure that we are viewing things using the game lighting mode. Let's also make sure that our skylight is set to static. Now this will possibly be one of the easiest lighting solutions that we will ever create, as all we need to do now is select our cube map of choice, which I've downloaded under a Creative Commons license from the hdri-hub.com website that allows us to also distribute the HDRI, which we can see right here in the content browser. Making sure that we have our skylight selected, we can change the source type to SLS specified cube map. After which we can click and drag on our HDRI in order to place it in the cube map slot. Meaning it is time to rebuild our lighting and take a look at the results. As you can see, we are getting some lighting in the scene, but nowhere near a level that would make us think that we are looking at a bright sunny outdoor scene, which is what the HDRI depicts. Let's crank things up then, setting the intensity of our skylight to a value of 10. Which will work by increasing the intensity of the HDRI that is mapped to it. And after rebaking our lighting, we can see that we have added a good amount of energy and detail to our lighting now. We could also increase our cube map resolution if we wanted, so as to get more quality from the setup. Although just remember that this has to be done using power of 2 values. And we do need to be cautious when upping the resolution, as this will, of course, increase our build times as well. We also need to keep in mind that it's no good increasing the HDRI's resolution if our light map resolution is left too small on our static meshes, as all of the settings that we have looked at so far in the course really do need to work together in a balanced way. Let's set our cube map to a high value of 512 then, and see if that makes any noticeable difference to the quality of our GI lighting. Once the lighting has baked, we can compare the results, and then make a decision as to whether or not the added bake time versus the quality improvement that we see has been worth it or not. Something that we could do then is lower the quality settings of the GI in the Lightmass controls, and then also increase the smoothing value back up to 1, as our skylight is now doing most of the work when it comes to picking out details in the scene. When we rebuild our lighting now, we see that we do indeed have a pretty decent GI solution, and once the scene is textured and the user is moving around, of course, any small problems that may still exist within the solution would most likely be unnoticeable. Making objects look like they belong in an environment will oftentimes be a must on visualization projects, and one of the tools that we can use to help accomplish this in Unreal is the Ambient Occlusion feature, with AO basically being a form of indirect shadowing. An overcast day, as an example, would be a typical scene in which we would expect to see lots of indirect shadowing. Helpfully, the Lightmass renderer in Unreal does calculate detailed indirect shadows by default, and so we have actually been getting and seeing ambient occlusion in the course with each light build up to this point. It is always good to know how to both turn such effects on and off though, should we ever want or need to, and also know how to adjust the settings associated with ambient occlusion in order to give creative control over the indirect shadows in the scene. Given that we have, as already noted, been using a post-processing volume in the scene as well, we have also been seeing screen space ambient occlusion applied as a post-process effect in each light build that we have made. The upsides to using SSAO, as it is oftentimes called, are that it is quick to calculate, memory efficient, and we get fairly decent results from it. The downside, however, is that it is calculated using just screen space, and so as objects roll out of camera view, they stop generating ambient occlusion, which can cause some very distracting pops and jumps as ambient occlusion on an object disappears from view. Ambient occlusion created by Lightmass GI, on the other hand, is baked into the light maps, and so will not only always cause objects in the scene to add AO, but will also appear to never pop, flicker, or disappear as the user navigates through the level. Although, admittedly, the ambient occlusion is not always as clean as we may perhaps like, and in some cases, such as with our scene here, may not work too well with thin-walled geometry. Although, in my humble opinion, and for a whole bunch of reasons really, we really shouldn't be using thin-walled geometry for our production visualization pieces anyway. Our O2_03 level is, at this moment in time, being lit with both a directional light and a HDRI, and has essentially had the screen space ambient occlusion option turned off by virtue of setting its intensity value to 0 in the post-processing volume. Indeed, in the first bake of the lighting that we are looking at now, if we press the 2 key to make sure that we are viewing one of the corners of the room, and then come to the World Settings tab and Lightmass options, we can see that our GI ambient occlusion option has also been turned off as well. Now the first option here, Use AO, will obviously enough enable all of the options that we see here, and so let's put a check in that and discuss the rest of the parameters that we have. If we rebake our lighting now, and then compare to our previous setup, we can see that we are clearly adding occlusion shadows to the scene. The next checkbox, entitled Generate Ambient Occlusion Material Mask, does exactly what it says, and creates an alpha representation of the AO for us, one that will need to be used with the pre-computed AO mask material node should we want to access and make use of it. Now we're going to look at some of the controls here, a little out of running order now, simply because, as we look down the list, we have a max occlusion distance parameter, which by default is set at a value of 60. This, in my honest opinion, is way too high for visualization pieces in general, and so is actually wasting some of our bake time, 60 Unreal units equating to 60 centimeters of course. Let's set this to a value of 8 then, which is still pretty high, and rebake our lighting. When we compare the two bakes now, we can clearly see the difference, as we now get a nice occlusion effect at what I would call an average or normal object distance. Now, the first option here that actually lets us control the amount of occlusion that we get would be the direct and indirect occlusion fraction options, that set just how much occlusion gets applied to objects that are being hit by both direct and indirect lighting. These act as a 0 to 1 percentage of the other controls that we will look at in a moment, with 0 applying no ambient occlusion and 1 adding the full amount. Let's set both direct and indirect values to 1 then, after which we can rebake our lighting. And now we can take note of how the occlusion is looking. Notice that these changes have really darkened up the AO effect as a whole. Of course, if we were to set both values at 0 and rebake again, we would effectively kill off the ambient occlusion effect. Now, we do need to keep in mind that because we have been increasing global illumination quality as we have moved through the course, our direct and indirect bounces are themselves doing a pretty good job of creating ambient occlusion, which is why we have had to make such a drastic comparison here. Let's set these to more realistic values of 0.3 and 0.6 then, and again rebake our solution. Next, we have the exponent control, which sets the contrast or transition phase of the occlusion effect. Now, this could be thought of as applying a levels control to the occlusion gradient. As we increase the exponent, the transition from light to dark becomes tighter, helping push our occlusion into the corner areas. Our current bake is using the project default value of 0.65, and so let's set this to a high value of 2 and rebake our lighting again. What we see as we compare now is that the occlusion has definitely shifted, which may be useful if we feel that things are spreading out a little too much. Now, we're going to leave this set at a value of 1.15 for the remainder of the course. As we do also have ambient occlusion override controls on post-processing volumes, you will need to make sure that you are keeping track of exactly what is affecting what in the visualization in order to get the best out of it. Before we move on to our Taking GI Further section, let's take a look at one last control here that can really help refine the work that we've done thus far. Before we do that though, it really should be noted that the feature we will be outlining here needs to be used with caution when working on interior visualization pieces, given that its intended use is to help us have fast calculating shadows when working on large-scale outdoor levels, using values of between 2 to 4. As its default setting is lower than this sweet spot though, it can clearly be used to squeeze more quality out of smaller scale scenes, such as our GI interior. Although, do be warned that this again will drastically increase lighting build times. To take a look at the option, let's come to our World Settings tab and make sure that we are looking at the Lightmass controls, where right at the top we see the Static Lighting Level Scale control. Now, before we adjust this, let's take a closer look at the current baked lighting in our 02_04 level by pressing the 2 key so that we are viewing a detailed area of our room. Remember that we are using our tweaked Lightmass settings along with the direct light and HDRI added to our skylight. As we make some adjustments to the Lightmass scale option then, I want you to keep an eye on the GI that can be seen in these hard to reach places, as this is where we are likely to see the most noticeable difference. What does the lighting scale control do? Well, the technical explanation is that it sets the lighting scale relative to the level scale, again remembering that Unreal works in centimeters, and so 1 unit is equal to 1 centimeter here. In simpler terms though, we could perhaps think of the lighting scale option as a way to tell Unreal how much detail we either do or don't want to calculate for our baked lighting solution. Smaller values would mean that we are essentially packing more lighting detail into a smaller space, thus increasing the overall quality. Doing this though, as with many of the other options that we have looked at here, will increase build times, and so, as again with many other settings, should only be altered by as small an amount as possible. In fact, unless we really do need to alter it, we should leave it set at default. So, how will changing this affect our GI solution then? Well, let's make the change from a value of 1 down to 0.75 and then rebake our lighting in order to see. As we compare the two results now, we can see that we are able to pick out more detail in the scene overall, but most noticeably in the occluded areas where our secondary bounces are providing all of the lighting info that we see. Let's push this pretty far then and go as low as 0.5, after which we can again rebake our lighting, which in this instance is probably going to take quite a while. Now, whilst I am using large value jumps here in order to help show the difference that the control makes, balance really is the key, and so we should be adjusting in small amounts here. After which we should bake and compare so as to make sure that we really are making a difference to the GI solution, adjusting again at that point if necessary until we eventually achieve the result that we want. Having decreased our scale, we can see how the GI solution is able to pick out even more details now, with the shadows on the floor being more defined than they were before. This does have a drawback that we can see in the scene though, as we are starting to make our GI look a little messy or noisy, meaning we would need to use the controls that we have looked at so far in order to get a balance of smoothness versus quality in the scene. We will continue to use the default of 1 for the rest of this course, but do feel free to use a value that works best for your particular project. If we are pushed for time on a project though, or if it is that we simply have enough machines to throw at the baking process, then adjusting the lighting scale is one way in which we can add more detail to our GI solution, albeit via a bit of a brute force approach. Whether a crowd of people walking around a shopping centre, a single person walking around their home, or even an animated product visualization piece, there will most likely be times when we want to add an animated object or objects to our project. As we know that Unreal actually bakes its global illumination into static light maps, does this mean that we can't actually have animated objects and global illumination both in the scene at the same time? Well, thankfully, the answer to that particular question is no, which is thanks to the volumetric light map feature that replaced the old indirect lighting cache in Unreal. What are volumetric light maps then, and how do they help us with animated objects and GI in a level? Well, coming to the Show button on our camera viewport, let's click to expand the option tree that can be found there, and in the Visualize Rollout, put a check in the Volumetric Lightmap option. We need to do this because in order for us to apply our GI solution to an animated object in a scene, we will need to access pre-computed lighting info that has already been baked into these sample points that reside in 3D space. Being able to see them allows us to judge the quality of our solution. The way things work here is that at runtime, as an animated object passes through an area associated with the sample points that we see, Unreal interpolates between the samples found around the object's travel path in order to create the illusion that GI is being applied to the animated object, as well as the scene. Probably the most important thing we need to know here is that these samples are automatically added whenever we create a Lightmass importance volume. In our level then, we have an animated object that if we just access our play mode dropdown and set it to simulate runtime in the viewport, we can see passes through the volume light samples and so gets the pre-computed lighting solution applied to it, with the engine interpolating between the various sample points as the object passes along. The problem here, though, is that we only have a few samples present in the room, and so the object doesn't really look like it's sitting inside the GI solution. Coming to the World Settings tab and Lightmass Controls, though, we see that we have Volume Lighting Method, Volumetric Cell Size, and the Volumetric Brick Memory in Megabytes option. The method selected by default is the feature's newer Volumetric Lightmap option, which works as already discussed. If we wanted, though, we could also employ the older Sparse Volume option, which uses the Indirect Lighting Cache. Now, this uses the CPU to interpolate between lighting samples, and has the drawback that we cannot use our GI solution to affect any volume fog in the scene. Let's change our cell size then, and see how this affects our object. Now, when we change the cell size though, we need to remember that we are setting the densest parts of the grid around our static meshes. As you can imagine then, this option has a big impact on build times, and so again, if we really don't need the extra quality, it is advised that we leave things be. For the sake of our training though, we are going to assume that we do need better quality for animated objects, and so for this particular scene, let's use a value of 100. As we increase the quality, we will also need to increase the number of megabytes allocated to the process. Otherwise, we could end up with Unreal culling information that we don't want it to, leading to very obvious, incorrect lighting being applied to our animated objects, something that we definitely want to avoid. I will just increase the megabyte limit to 50 so as to be safe. Once we bake our solution, and then preview the level, we can see that as our object passes through the scene, we now have a much better representation of the GI on the object, simply because of the lower grid size. Again, looking at the bottom of the legs, if our character is the focus, then we might want to increase the detail by lowering the cell size some more. A value of 50 works well for this particular scene. It's good to note also that the volume light samples can also be used to generate good-looking volumetric fog, which we will hopefully be able to cover in a more advanced Unreal rendering course. As we will always want the hard work that we have put into our global illumination solutions to look good, knowing how to handle animated characters and our objects can sometimes be as important as knowing how to get GI to bounce around the environment in the first place. After putting all of this work in so as to create a good baked GI solution, we may at this point in the project want to use Unreal's post-processing effects in order to make things look even better. Of course, as we've noted, we have already been using a post-process volume so as to make the adjustments that we have made to the GI controls easier to see. In this version of the scene, however, we've deleted the volume so that we can demonstrate how to work with one from scratch, as it were. To add a post-process volume, we can come to our Modes tab, type the word post, click and drag a post-process volume into the level, and then zero out its transforms so that it sits right in the center of the world. Now in this case, we will use just a single volume for our entire room, but we could quite easily use multiple volumes even inside the same room if we wanted. What exactly does a post-process volume do though? Well, we could perhaps illustrate it this way. Imagine, if you will, that you could tag the various rooms in your home so that when you walked through them, filming or shooting with your camera, an automated system tracked you and updated your camera settings on the fly in order to always give you a perfect exposure based on both the current lighting conditions in the room and the point at which you were standing. Now, although we can for sure control exposure inside the volume, something that we will take a look at in another video, we can actually do a whole lot more besides, such as controlling anti-aliasing, tone mapping, chromatic aberration, and much more. Let's set our volume's position to 150, 0, and 135 then, and set its scale so that it encompasses the room, so 2.5, 7.25, and 2.5. And then take a look inside the Details tab at a few of the settings that can help us adjust the look of our GI. In the Rendering Features rollout, we have a Global Illumination section that, once expanded, houses controls that allow us to add a colour tint to the GI. Putting a check in the option lets us use either the RGB value controls, or we can click on the colour swatch to access Unreal's colour picker options. As we change to a warmer colour, you can see how the volume changes our camera's perception of the GI in the scene. Just be aware here that we aren't actually changing the baked lighting maps in any way at all, meaning we can always get back to our original solution quite easily should we want to. Obviously, we can craft the look of our GI on a per volume basis, so if we feel that we need a warmer look in some areas of the visualization, all we need to do is add a volume and make the change, all without having to rebake our lighting or find ways of warming up the GI solution at source. We can even use the saturation value controls to fine-tune the colour once picked. Let's click OK, reset the result, and then take a look at our second option, the Indirect Lighting Intensity control, which we can again put a check in. This option is probably fairly self-explanatory, but again, if we had a building with multiple rooms, all of different sizes, we could find that the GI in some of the smaller areas was too bright, simply because we had to ultimately balance the solution out based on the larger spaces. What we can easily do now, though, is place a post-process volume and lower the intensity of the pre-baked GI inside of it. Of course, the opposite is also true, in that we can just as easily brighten up the GI if we needed. Other effects such as bloom, vignetting, and ambient occlusion can all be added on a per volume basis as well, meaning we can craft our client's visualization experience on a room by room or zone by zone basis for perfect results. With our post-process volume in place, we also now have the ability to adjust our camera's exposure settings on a per volume basis, meaning we can make sure that each area of our visualization piece will automatically look as good as it possibly can whilst our client is walking around it. Making sure that the post-process volume is selected in the world outliner then, we can do a search for it if we need to. We can come to the lens rollout and find the options that we want under the camera and exposure headings. As we look at our options here, we may ask, what is auto exposure? Well, this particular effect, sometimes referred to as eye adaptation in Unreal, mimics what our eyes do naturally when we, for instance, walk from a bright exterior to a darker interior, in that our eyes adjust so that we can quickly make out details in the new lighting situation. In order to see the changes that we will be making here, let's put a check in all of the options that we have, except for metering mode, and then work our way down the controls. Min and max brightness pretty much speak for themselves, so if we set our min brightness to a value of 1 for example, our camera's exposure will never drop below that value. In fact, a workflow that I like to use when setting up lighting and GI is to set both the min and max values with the same number, essentially giving myself a fixed exposure that doesn't change when looking from bright to dark. To demonstrate how the system works by default though, let's find a dark space in our level, and then set both controls to a value that lets us see all of the detail found there. So, a value of 0.1 should do nicely, which as you can see, causes our viewport to brighten so that we can clearly see the scene. Let's just write that number down, and then move the view over to the brightest part of the scene, so maybe this small unit under the TV. And this time, try working with a value of 1. Now, this does make the rest of the scene look very dark, but it does ensure that our client will be able to see every detail very clearly when looking at areas of the scene in direct light. Now, we are using some fairly extreme settings just for demonstration purposes here, but as with all things artistic, the choice of exposure setting that we ultimately make will depend on exactly what it is that we need to accomplish with the project that we are creating. And of course, the values used will also depend, at least to some extent, on light intensity settings in the scene. So, if our sun, for instance, is set to an intensity value of 1000, then we would probably need to use exposure settings of 80 and up. In this instance, though, I'm going to set the min brightness to 0.1, max to 0.9, and then again take a look at the darkest and the brightest areas of the scene, which, as you can see, causes our viewport to automatically adjust its exposure now so as to compensate for the shift in illumination levels, with the speed up option controlling transition speed from dark to bright, and the speed down option controlling bright to dark. If we set them both to a value of 8 and then look from bright to dark and back again, we can see this in action. Now, this is way too strong and distracting an effect, of course, but you can clearly see the effect it has. Let's go back to the defaults of 3 and 1. Finally, the exposure compensation option lets us add a logarithmic adjustment to our overall exposure, a logarithmic scale being used whenever there is a large range of quantities to be encompassed. When it comes to exposure then, a bias value of -1 will make our scene half as bright, whereas -2 will make it a quarter as bright. The same being true of positive numbers. 1 is twice as bright, whereas 2 will make it 4 times brighter. Given that the exposure settings we use will have a direct impact on how the end user sees the GI solutions that we create, being able to adjust this on a per volume basis gives us a fantastic level of control that can again only help ensure that every inch of our GI solution looks as good as it possibly can. If we are used to producing images in offline render engines such as V-Ray and Arnold, then we will probably be familiar with the color bleed effect that comes along for free whenever global illumination is used in an environment. We see this because as light rays bounce around the environment, they both pick up and deposit color on various surfaces that they strike. When a photon hits a surface that has a high color saturation, for instance, then the color is collected, but when the energy of the photon gets absorbed by another surface, it leaves color behind. Hence color bleed, or color bounce as it is oftentimes called. Because of this naturally occurring phenomenon, we may at times find that our scenes have picked up a distracting color wash, or going in the other direction, that it doesn't have enough color bleed in order to either look realistic or suit our needs. The question then is, how do we actually go about controlling color bleed in Unreal? Well, in our 03_04 level, our objects have a variety of plain grey materials applied, which, as you would expect, has produced a monochromatic GI solution. Having applied a red material to the floor, though, watch what happens when we go ahead and rebake the lighting. We see that because of the saturation value on the material, our entire scene has been somewhat overpowered with a red wash, which, whilst possibly being physically correct, may, from an artistic point of view, not be quite so desirable. Let's access the material's properties by double-clicking on it in the content browser then, and take a look at the options that we could use to dial this down a bit. Well, we could lower the saturation of the base color on the material, as that would in turn reduce the color bleed effect. But what if we, or our client, really likes the particular shade of red that we have? Well, thankfully, we can actually perform a GI switch in Unreal at the material level. In other words, we can use one color on the visual mesh and set another to be used for the GI light bake. Let's right-click in our material graph then, type the letters GI, and add a GI replace node. We can pipe our Vector 3 node into the default slot, which will be the color that we see on the object. And then copy the color node, and pipe it into the static indirect slot, which is the color that will be used for the GI calculation. If we then click on the color swatch, we can make some changes to this. Now, to keep the illumination levels in the scene as they are, we will want to leave the value as is, although altering this is one way in which we can control light bounce on a per material basis. But as what we want to do here is just dial back on the colour bleed effect, we want to lower the colour's saturation by about 75%, so a value of about 0.35-ish. After which we can save, apply, and then close the material editor. Now, personally speaking, I think that removing all colour bleed from a scene only leads to creating an unnatural looking environment, as our brains know that a bright red floor should kick at least some colour around the room. But I will of course leave that artistic choice up to you and or your clients. Let's rebuild our lighting then. And as you can see, whilst we still have our saturated red floor, the colour bleed or colour bounce coming from it is nowhere near as strong as what we had before. Now, another way in which we could control colour bleed in Unreal would be again to access the material, and in its options, perform a search for the word diffuse. Notice that we have this Lightmass specific boost control that lets us fine-tune how much this particular material will contribute to static lighting in the scene. Do be aware though that using this option, although reducing colour bleed, also reduces how much the material contributes to the lighting solution itself. In other words, as we dial this back, we will get less illumination in the scene and so consequently a less realistic lighting result. Being able to control colour bleed then can certainly help us art direct and tweak our finished GI solution until it feels just right for our needs. Sometimes on a project we may have need of a mechanism that lets us quickly switch between natural and artificial lighting setups in order to show a client how their space will look under very different lighting conditions. Obviously, we won't want to have them sit and wait while we rebuild a lighting setup. In fact, we may not even want to have them wait while we load a different level during a presentation, which is where lighting scenarios can come to our aid. How do we go about setting up lighting scenarios in an Unreal project? Well, the very first thing that we need to do is create sub-levels containing the various lighting setups that we want to turn into scenarios. We create new levels by coming to the window menu and clicking on the Levels option. Inside the dialog, we can click the Levels drop-down and then select the Create New option. If we have already created our levels using the File menu at the top of our Unreal UI, then we can simply click and drag them from the content browser and onto the persistent level. Into the Room No Light scene then, we can add two new levels, one called Day_Light and the other being Night_Time. Now, hopefully the lighting setups that they contain will be self-explanatory, but all we really need to know is that we have two extra levels, each with a lighting solution that has been baked out. Let's drag both of them from the content browser then in order to add them as sub-levels. If we right-click on our first level, we see in the options that appear that we have the ability to turn this sub-level into a lighting scenario by coming to the flyout of the same name and clicking on the Change to Lighting Scenario command. Whenever we make a lighting scenario level active now, it will be the light maps contained in that level that gets applied to the persistent level that we are viewing, meaning we can easily switch between lighting setups whilst at the same time keeping everything very performance friendly. We can even control exactly when it is that a level gets streamed via a blueprint, and so let's right-click once again on the sub-level, set its streaming method to blueprint if it isn't already, and then take a moment to perform these same steps for any other sub-levels that we may have. Having created the levels that we want to use then, time to create a small blueprint that will allow us to quickly and easily switch between the lighting setups or scenarios that we have. To do that, let's open up our persistent level blueprint, which we can do by clicking the small game controller icon found in the levels dialog box. And once open, right-click and type Load Stream Level into the search, adding the node of the same name when we see it appear. With the node selected, we can press the Ctrl+W keys to create a duplicate, and then right-click again and search for and add a flip-flop node, which, as the name perhaps suggests, lets us switch back and forth between two different outputs. Let's right-click again, type Unload, and add an Unload Stream node to our graph, and also create a duplicate of it. Let's pipe the A and B outputs into our unload stream nodes, and then pipe their output into the level stream nodes. And after right-clicking one final time, let's type key in the search field and add an L key node. We want to type the names of our sublevels into each of the level stream nodes, so day_light in one and night_time in the other. And then add the opposite names to the unload node that precedes it, so night_time and day_light this time. To get our lighting scenarios to load, we will have to put a check in the Make Visible After Load option, after which we can compile and save our blueprint, and then run the persistent level. Once booted up, we can press the L key to load our first alternate lighting solution, and then if we press L again, we can switch to the other. Saving out lighting scenarios then means that we can have multiple lighting and global illumination solutions already baked out in a project, and then quickly and easily switch between them inside the engine. A very handy feature for visualization pieces indeed. Although we can, of course, use Unreal to create real-time, interactive and VR walkthrough or look-arounds of an environment, some projects that we work on may require that we create high-resolution still shots as well. In this final video for the course then, we will look at creating a final setup that can be used to create high-res day and night shots of our scene, and then of course look at how we can save those shots to disk. With the final_day_light level loaded and being viewed in game mode, and with the cinematic viewport option turned on, let's take a look at what I've done to this version of the scene in order to get things ready for the final shots that we want to create. Our directional or sunlight then has been given an intensity setting of 9, and we have it set to static in its mobility options so that we can have area shadows in the scene, with these in turn being controlled by a light source angle setting of 1 and an exponent of 4. We have a skylight, of course, with an intensity setting of 5, and this is using a HDRI that has a resolution setting of 128. We have dropped in some spherical reflectors in the scene that, although not altering the lighting in any way, do allow for more accurate reflections in our materials. The materials themselves having been tweaked to fit more in line with the concepts that we discussed in section 1, with normal intensity and scale also having been tweaked. Coming to our important Lightmass controls, we have been able to pull more detail out of the solution that we have by increasing the quality settings that we see here, something that we can safely do because we only have a single room in the project, which, even with everything turned up, still runs nice and speedily at runtime. The static lighting scale has been dropped to 0.9 to help create more defined areas of shadow in the indirect lighting. And as sunlight is the main focus of the lighting, we are using 10 light bounces in the indirect control, whilst the skylight, which is being used as a fill light, is set to 8 bounces. Again, to help draw out extra detail, the quality and lighting smoothness for the indirect options have been set to 1.25 and 0.73 respectively, with the first value adding detail in, and the second making sure that we aren't smoothing or blurring that detail back out again. Ambient Occlusion is being used with settings of 0.4 and 0.6 for the intensity, and an exponent of 1.15, so as to push it into the corners a little more, along with a distance value of 8. Coming to the post-process volume, we have taken some of the edge off the bright highlights here by, in our color grading controls, setting the gain value to 0.6. Our exposure has been set to look good in both stills and real-time versions of the scene, with min and max brightness values of 0.07 and 0.1 helping us see detail no matter where we look. In the rendering features, we are adding screen space ambient occlusion as well, just to help with areas that our GI may have missed due to low-res light maps. And this has an intensity of 0.2 with a radius of 10. An atmospheric fog from the Modes tab was added after the light build just to give us something to look at outside of the window, besides the black and unnatural looking void that we had by default, with none of the options having been changed. If we press F11 at this point then, and use the 0 through 4 keys, we can get a sense of how the scene is looking and the composition of the shots that we have created. The question now then is, how do we actually go about saving high-res images out of Unreal? Well, if we come to our viewport dropdown, you can see that we have a Take High-Res Screenshot command, which when clicked, gives us access to a number of options. If we save a screenshot, right-clicking on the file shows that we have saved a 1000 by 500 image. Let's increase the output size a little by setting the screenshot multiplier to 3, and then clicking to save again. Now, whilst that is a quick and easy option to use, let's try being a bit more specific about what we want to output. With our viewport highlighted then, let's press the tilde key, type the word high res, and then click to fill in the command, and then add a space to the string and type 4096 by 2160 and press enter. If we click to load the folder now, and then right-click on the file and choose the Properties command, we can see that we do indeed have a 4K image saved to disk. And if we open that up, we can see what that looks like. We also have a nighttime version of our level, of course, that has had some adjustments made to it. And so let's load that. And then press the G and F11 keys to again cycle through our camera bookmarks. What we see here is a level being lit by standard spotlights set to static mobility and using a source radius of 8 for the area shadows. Pressing F11 again and then searching for and selecting the post-process volume, we have made adjustments to only the exposure here, having turned off all the other settings that are found except ambient occlusion, that is. To balance the bright and dark areas of the scene, we are using a logarithmic exposure compensation of -0.9 just to help dial back on the overall bright highlights. We have also adjusted the min and max brightness values to 0.03 and 2, and have increased the transition speed by setting the speed up value to 8. The Lightmass settings for this version of the scene are somewhat lower than the daylight ones, and the static scale has been left at the default of 1. Light bounce from the spotlights has been increased to 15, just to help push light around the room, and the skylight has been removed altogether. The indirect lighting quality and smoothness settings have been lowered, as there isn't really the need for quite as much detail here, with values of 1.15 and 0.79 working pretty well for the scene. Having applied all that we have learned throughout this class to these two levels, we can hopefully see that getting good quality global illumination solutions is perhaps not quite as difficult as we may have first imagined. We should keep in mind that these settings will need to change on a per project basis, given that the size of a room, the amount of rooms, and object density in a scene will all play a part. But if we remember to apply the knowledge and principles that we have covered here, we should be able to create a good-looking GI solution no matter which type of project we get to work on. Now that we have created, refined, and even embellished a GI solution in Unreal, you may well be asking, what comes next? What can I do now that will improve my skills in this area of the engine? Well, the very best place to start is practice. By putting into practice the things you have seen and learned here, you will be able to lodge the principles that we have covered very firmly into your mind. To that end, go and grab a project or level of your own, maybe a new one, maybe one that you have created and used in the past, and see if you can either create from scratch or improve on the lighting solution that you already designed. Try going even further then by experimenting with very different lighting conditions and setups. So maybe trying to get a good GI solution out of a dusk or sunrise setting, as well as out of a more general daylight scenario. Another exercise to try would be to create a GI solution for just a still shot, making it look as good as it possibly can. And then, keeping as close as possible to the already established quality level, try making that level run in real time, in a completely smooth way, balancing performance and quality using the controls that we have already looked at. Well, it has been my pleasure to have you work along with me in this class, and so I would like to take the time to say thank you very much here. And until the next time, this is Joel Bradley saying take care and bye for now.